and check out these two. And by a few minutes, I mean that. We won't take forever with this. And then we'll get back into kind of more regular discussions and moving forward. So go ahead and start there. Okay, so here are the answers for the graph match. So please go back and check your graph match out. See if we agree on stuff. Maybe there's some disagreements. Some good opportunities for discussion. Some of them look really similar. Square roots and logs and exponentials. And some of them look similar enough it could be confusing. Please look those over. Hopefully, looks fairly readable. Thoughts or questions? I hope that as we kind of get to know each other and get the culture of our class going, I hope that open discussion is okay. Just a kind of an FYI for you guys, I'm working on my master's degree right now. I've got 2 classes left. The stigma of asking a question does not go away with age. Right? People tend to hesitate to ask a question because they don't want to look dumb. Right? It's like if I raise my hand and ask a question, I'll probably look stupid because likely everyone else knows it, and I'm the only one that doesn't know it. And you know that the opposite is usually true, right? Usually when you ask a question, you're asking the same question that like 3 or 4 others probably had as well. And you know what? Even if you're the only one, who cares? It's about your learning, it's about your education, not about your image. And so I encourage you. Just know that I'm the one in my class. I don't hesitate for a minute to ask questions. In fact, I just started a new class this weekend, and my first question was like, where the heck do I turn things in? Because I couldn't see where to turn things in, and it turned out it was not very clear at all. And so if I had not asked that, I would not have known, and like half the class would have known either. So don't hesitate. It's okay. It's okay to say, I don't know the answer. Okay, nobody knows everything. So it's okay to ask. So I tell you that story to invite you again. Does anybody have any questions on this whole graph match thing? Some of them are a little confusing. Yeah, Luke, go ahead.
Why does a cube root function look like that? Like we inherited that?
Oh, but like by process of elimination?
Yeah.
Sure. So I think that you could approach it a couple of different ways. One of the obvious and weakest ways would be you could obviously plot the points, right? But I would say kind of a cool connection is this, to look at a comparison of this graph with that one, right? So if we said y equals x cubed and y equals x to the 1/3 and tried to compare those, would it be fair to say that those are actually inverses? Think of it like this. Like if we started off with y equals x cubed and we wanted to find the inverse of y equals x cubed, isn't it kind of your typical first step with these really simple inverses to flip the input and output and then solve for y? So I'd cube root both sides. So I'd get y equals the cubed root of x, which is the same thing as x to the 1/3, right? So hopefully that would be a proof that y equals x to the 1/3 and y equals x cubed really are inverses of each other. Then, graphically speaking, do you guys remember how inverses relate on a graph? Yes, the reflection over the y equals x line. So this is y equals x cubed. And so if I will do my best. If I drew that y equals x line, that's actually sort of decent. Can you see how if you reflected all these points over that, you would get that same graph? Like if you took this point and reflected it across, like you took this point right, there, reflected it across, you'd get like that right there. And, this one here reflected across, it'd be like over there somewhere. And you can start to see how this point here, this point would actually be up there. And we're starting to get this fairly decent representation of what you already see over there on the left.
That'd be another way to look at it, graphically speaking. Okay, great question. So the questions don't always have to be like, I don't get it. Like if that's your question, that's fine. But that was more of like, I think we figured this out, but why? I love those questions, right? Or what if questions. What if it was this? Would that make a difference? And sometimes I'll know exactly what to answer you with. And other times I'll say, what if? I don't know. That's a really great question. We should probably think about that some more. I don't know. So, thank you. Anybody else? Okay, fair enough. So then let's take a look at the limits part of the warm-up. And that is over here. I'll just show you the answer part, and we can zoom back out and look at the graph if we need to. So how about that? Just a note, if the answer to one of these limits could be infinity or DNE, right? Because technically infinity is not a real number. We talked about that a little bit last time. The answer could be infinity or DNE. I will always put infinity because I feel like that's a better descriptor of what's actually happening. But if for A you had DNE, I would never mark that wrong. If it was a multiple choice, like let's say that A was multiple choice, I would never give you both DNE and infinity as options. I would give you probably infinity as the correct option. Is that going to be the answer? So, anyways, so there's those. Again, same deal. If you have questions about any of those, even if it's just a what if question, let's talk. How are we doing? Okay, so let's make sure we all understand where we're going with this. So review quiz 1, Wednesday. So far there are only 3 question types that are even eligible beyond that. That makes sense? The ones we did Friday and the graph match. We have another warm-up with potential RQ1 stuff tomorrow. And that'll be kind of your first big grade, if you will, of the semester. Okay, so if you guys are ready to move on, we're actually going to go backwards a little bit. I want to catch that last question that we did not get last time, and it is back here. It's number 3 on Unit 1, Day 1. And like I said, I'm really hoping that today, by the end, we'll have completed Unit 1, Day 2 and gotten all done so that we can continue on the more planned out pace. But if you would, feel free to use your calculator on this one. That might be beneficial to help you see the stuff that I want you to see. But please try number 3 here. We'll treat this again as kind of a discussion group effort, and then we'll get some answers and hopefully some good conclusions by the time we're done. So create a table, and more particularly perhaps a graph, in an attempt to evaluate that limit.
Makes sense.
I haven't looked at every single detail in all the papers, but I think we more or less agree. If we were to try to evaluate that limit, just shout it out. What do you think the final answer would be? DNE. Yep, I agree with you. This does not exist. This limit does not exist. And let's take a look at a couple of different levels of communication. As far as maybe you were asked to give a reason for your answer. If you were just going to say it, like just verbalize it, what would you say the reasoning would be? Any thoughts? Hunter, go ahead.
As x approaches 0, the graph approaches 2 separate numbers.
Yeah, so different behavior, right? From the left and the right. Yeah, that's a good way of putting it. What if we wanted to get a little more formal and take what Hunter just said and describe it a little more accurately? What if I said the limit as x approaches 0 from the left of that expression? From the left, what's the value we're approaching? -1. And then from the right,
1.
we're approaching 1. Also correct. Okay, so since those two, now check this out. Since those two one-sided limits are equal to their numbers, right? -1 from the left, 1 from the right. We can say those two one-sided limits are not equal. Isn't that a more precise way of saying different behavior from the left and the right? And we're gonna really want to transition towards this really good thinking here. Okay, so I should say really good communication. I think the thinking was already pretty good, but this is better communication. From a graphing perspective, did you basically get kind of a stair-steppy looking graph? So I'll do this in orange. So from the left we have this, and you got a double open jump like so. Is that about what that looked like for you guys on your calculator? Okay. Yeah, and so this is, of course, -1, this is 1, and we get that different behavior from the left and the right. So ultimately the answer is the limit does not exist. This is really nice communication, and we're going to really work to try to speak that kind of language in our communication here as we get into this. Okay. And of course you could have done a table, and basically the table is either going to be, the outputs are either going to be 1 or -1 or DNE, right? Right there when x equals 0. So there's more to say there, and unless you ask a question, I'll leave it at that though. Any questions, any thoughts there? Okay, so I think this first thing we're going to do here is, let's go and transition over to Unit 1, Day 2. I think this first item we're going to tackle is something that's going to look a lot more familiar to you, and it's right here, number 1. Says, evaluate using any method, and let's try to avoid using the calculator here, and let's use more of the methods that you probably learned in pre-calculus. See if you can use those, and we're going to really focus in on communication here on this one. But try number 1, using, like I said, kind of those pre-calculus-like skills that you practiced last year. I can see that you guys are either done or you've made really good progress and you're almost done. So I think we're to a point now where I'd like to show you a solution. And like I said, I'm going to really focus on the communication. Yeah, I'll focus on the communication. I'll give you maybe an illustration to help you remember. Okay, so whenever you're working on a limit like this, your pre-calc teachers probably told you this, and they were right. Isn't your first and perhaps your best strategy just to plug in the number? And if the function, we'll talk about this later, if the function you're dealing with is continuous at that point, then that's going to work, and it's going to be over with really fast. That's great. If you try that here, though, you can see that immediately you run into an issue, and what is that issue?
0 in the denominator.
0 in the denominator. We have to work some way of dealing with that, right? And so the way that you learned, often pre-calc students will learn factoring as one of the big methods that you can use, and that's going to be the case here. So I'm going to show you some really good communication. You want to see like the good example first, or like the flawed communication first? Want to see good first or bad first?
Good.
Good. Okay, I'll show you good first. So if I were going to do this, I would write something like this. Limit as x approaches -1, and then I would attempt to factor the numerator, because that certainly looks like it could be factorable. And to be honest with you, I'm going to try to be really smart about this, because the truth is, if the top factors, and this is going to work nicely, isn't one of the factors going to have to be x plus 1? So I'm just going to put x plus 1 there as one of the factors and hope that I can make the other factor work, because if I can, I'm good. If I can't, then maybe some other method is needed, or this just is simply not going to work well. So I look this over, and I realize this would have to be a -3, this would have to be a 2x, and the other thing I have to really do is check to make sure that my middle terms add up to be what I want, and I think they do, right? Looks like it factors nicely. You can see now that this cancels out, and so I'll write limit as x approaches -1 of 2x minus 3. And then once you've done that canceling, can't you just retry the whole plug it in routine? Yeah, and so here it does work, and you get -5. So if you wrote this out, and this was your solution, I would definitely give you full credit. No issues at all. I think there would be one more little tiny step that would show that you really have a better sense of what you're doing, and that would be, like Merrick, to tie this back to the very start and say, hey, I got this limit, therefore the limit of my original, the one that I was actually asked to find in the very beginning, is the same thing. So up to this point, for sure, full credit, no problem. If you go beyond that, we'll call that like major brownie points, right? You've understood, you've done it well, it's all awesome. Can I give you an example now of some bad communication? Okay, so I want you to really reflect and think about Did you follow the good communication path or the bad communication path, or was it sort of a mixed bag? You never know. So here we go. This would be an example of not so good communication. Why should it actually be that? What's so bad with the thing in red?
Because even idea what you just solved was.
Yeah, it's pretty confusing. Like if you really stop and think about it, it's really confusing what's happened here. Here's why. Like I can clearly see that you took this and you factored it. Great. Now the limit's gone, and in math, think about this. Isn't this the convention in math? When there's some symbol there, whatever that symbol is, when that symbol goes away, it disappears. Aren't you telling me I did it? Whatever the symbol is telling me to do, when it goes away, I did it, right? Like if you're squaring something, like when you actually square it, doesn't that little 2 that was up there, isn't it gone now? If you square root something, like square root of 100 isn't square root of 10 because the square root symbol should be gone because you did it. So if that limit goes away, what are you telling me? I did it. It's gone. I've done what that symbol told me to do. And so it's gone, and so I'm thinking to myself, all right, it's gone. They clearly have done something with that limit. It's gone. So then we get to this step, and I can totally see, yep, you canceled. That perfectly makes sense. This now makes sense. And then what on earth did you do? How did 2x minus 3 just magically become negative 5? Your communication is very weak, right? And so that's why I would say that red side, obviously negative 5 is that final solution that we're looking for this particular expression, or the final value for this expression, but the communication is extremely weak. You would not get credit for the red effort. If this were the quiz 1 on Thursday, I guess it would be, and you had this question and you did the thing in red, I'm not even going to think twice. Wrong. Okay? But if you did the thing in blue or even up to that horizontal line, full credit, no problem. Okay? So isn't it really bad when a teacher is unclear about something, and then later on the thing that they were unclear about, you get nailed on the quiz or the test or whatever? Am I being clear about what I expect? I hope that I am. That's my intent, is to be clear here. Okay, so let's just take a minute and do this, because some of you might know this. Down at the bottom of the page it says something like, what's actually happening when you're canceling out these factors? Let's just discuss this real quick. From a graphical perspective, like when you cancel factors, do you guys know what's happening? There's a hole, that's right. So, believe it or not, if I were to graph this, and you can confirm this if you want later on, if I were to graph y equals 2x squared minus x minus 3 over x plus 1, anybody know, without, maybe you already did graph this, I don't know. Did anybody know what that graph would look like on your graphing calculator? It's a straight line, and what's the slope?
2.
And the y-intercept?
Negative 3.
That's exactly right. So it would show up on your calculator, it'd show up about like this. And if you have the color calculator, you might be able to see this, but that wouldn't really be the most accurate graph, would it? What feature would be on the graph that you may or may not be able to see on the calculator?
A hole.
A hole, and where would it be? At -1, yeah. So you'd have this lovely hole in your graph at -1. Like I said, you may or may not be able to see that in a calculator. This would be an example where your calculator might tell you a little bit of a lie. It'd make it look like a line, but it's really a line with a hole in it. It'd look like that. Well then, what would happen if I graphed this? Yeah, that'd be the line just with no hole. And so when we cancel factors, like you all said, we're creating a hole, a graph with a hole in it. And wouldn't it be fair to say that those two graphs, the red graph and the blue graph, they are exactly the same in every possible way, except at that one point, at x equals -1. And because of that, I can then use that blue graph as a way of saying, okay, well, here's the pattern in the y's. The pattern in the y's is clearly -5. We get it. There's a hole there, but the pattern is still the same. That's all we're really doing. We're creating a graph that makes it a little more helpful for us to evaluate. That's it. Okay, so for those that maybe had poor communication, I wanted to give you one more chance to try to practice good communication. So if you'd flip over to number 2, it's a very similar question to what we just did. Like I said, I want to give you a chance to kind of rewrite that part of your brain and do some good communication. So try number 2, see if you can do a little bit better if you need to improve. Okay, I'm seeing some awesome stuff. So really similar strategy. Factoring is going to be the right way to go here. What factor is in the denominator? That's right. So you factor out the x in the bottom, you get an x plus 3 as a result. Now everything is factored, so the x's would cancel. Oops. And so then you end up with the limit as x approaches 0 of 3 over x plus 3, or no, 2. Typo time. There we go. And now you can directly evaluate. You get 3 over 2, and that, of course, is exactly equal to that original limit. So you could do something like this to clean it up and say, this is my actual answer. Again, just to be clear with expectations, everything in the highlighted box, if that's what you wrote, I'd give you full credit. That last little piece is just kind of a FYI. I'm actually answering the question. So there you go. Any questions on the communication? I feel like you're all pretty good at the factoring thing, but communication, right? Sometimes that's the issue. Okay. So this last little piece here are just some properties of limits, and we'll go through these. We'll go through this one pretty quick. These properties of limits are probably all things that you would expect to be true. For example, the limit of a product is equal to the product of the two limits. The limit of a sum is equal to the sum of the two limits. The limit of a quotient is equal to the quotient of two limits. In other words, you can apply that limit to the individual pieces of the expression that you're dealing with. This is not going to be true of everything that we do this year, but it is true of limits. All these are true provided that the limits actually do exist. If either one or both of the limits is a DNE or an infinite something or other, then we got to rethink things. We might have to take a different strategy, or the limit simply might not exist. This is all these rules are dependent on the limits, both of them actually existing, for us to be able to use these properties. So with that in mind, I'm not going to read through all these, kind of an information download. I thought we would do one example here today, and we'll do another couple over the next few days. So for this number 3 right here, what are we looking at? Are we looking at scalar multiple, sum difference, product, quotient, power? What am I trying to illustrate with number 3? Quotient, right? It's the limit of a quotient. So I want to start you off on this, and then I'll let you run with it. So the first thing you could write if you wanted to, I think this would be good communication again, is you could say, really what we're going to find here in the end is the limit as x approaches 2 of f of x divided by the limit as x approaches 2 of g of x. Right? So the limit of a quotient is equal to the quotient of these two different limits. And then you've got the table to help you figure out the limit for g of x, and you've got the function rule there to help you out with the limit of f of x. So again, take a moment here, see if you can round out and finish number 3. We'll check your answers here in a second. Good communication here. Let me know if I communicate poorly, and I'll try to fix it. Would you guys be okay with this if I said equals, and then for my second step, I just put a denominator of 3, just like right from the table? Now, we can't be for sure that the limit as x approaches 2 of g of x is 3, but based on the table, that seems to be the most reasonable answer, right? So the numerator, maybe you did some factoring and canceling off to the side. After you do the factoring and canceling, don't you end up with this? And once you've done that, now the evaluation of that limit is pretty straightforward. You would, of course, get 1/7 over 3. And believe it or not, if this was an open response style question, like not a multiple choice, you could leave your answer just like that. Of course, this is 1/21st. That works too. But if you left it as 1/7 divided by 3, I know that that breaks all kinds of like rules you learned in Algebra 2 and maybe pre-calc, like you can never leave an answer like that. I don't care. It's okay. If it's equivalent, we're good. You need to be able to know that that's actually 1/21st, but I'm not going to like ding you on points for something like that. Okay, how are we doing? Okay, we've got a little more thing to do here before we finish out. And I think I want to go in order here, and we'll see about 5. I hope we get to it. I want to talk number 4 over with you. So looking at number 4, can you guys identify in number 4, can you actually find the directions where it says, hey, students, we want you to find this? Isn't it like right here? Okay, so they're asking us to find this. Isn't the truth here, like if you read this over, haven't they given us very little information about f of x?
Yeah.
Like almost no information at all. They've told us a lot about 4 minus x squared. They gave us a rule for that. 4 plus x squared, that's all hanging out there. But they have told us, other than that, nothing about f of x. So it'd be understandable if you looked at this and said, I have no idea. I don't know how to do this. But when you do look back here at the start, can anybody express maybe graphically what that means? What would that mean on a graph? How does that relationship work? 4 minus x squared, which by the way is what on a graph? Parabola opening which way? Opening down, yep. 4 minus x squared is less than or equal to our mystery function, which is less than or equal to, and what's the graph of that second thing? Parabola opening up. Maybe, to help you, since nobody jumped on the how do these things relate, maybe we should graph the two parabolas. See what that looks like. So here is parabola number 1. And here's parabola number 2. Do you see how they would both meet at 4, at y equals 4? They would have one little intersection point right there. So based on that now, that the downward opening parabola is always less than or equal to our mystery function, which is less than or equal to our upward opening parabola, what does that mean on the graph for f of x? Okay, and what about the rest? How would you describe like the vertical relationship between the two parabolas and our mystery function? If the red parabola is always below our mystery function, and the blue parabola is always above, not necessarily a line. Sure, yep, and that's what we're going to get at here, but the relationship. Oh, we're out of time. I hate it when I have to answer my own question. Let me put it to you like this. Isn't our mystery function always between those? Right? The downward opening parabola is always lower. The upward opening parabola is always above. So I have no idea if my mystery function is a line or what it is. So I'm not going to draw it as a line. I'm just going to say that it's this. Don't I know for certain that it's somewhere in between vertically? It's got to be, right, based on that statement at the start. So you guys all kind of zeroed in on it. If it really is in between, as we get closer and closer to 0, doesn't my mystery function have to be approaching a value of 4? Yeah, that's right. So I think based on all this reasoning, we could say the limit as x approaches 0 of f of x has to equal 4. And this is an important enough concept that it has a name. This is called the sandwich theorem or the pinch theorem, because can you see how our mystery function is being pinched by the two known functions, sandwiched down? Okay, so I'm going to do this. I usually don't try to race through, but I'm still fighting the 40-minute stuff that we had at the start of the year. I want to do this last one. I have about 1 minute, and I think it's going to take me today about 1 minute. And I'm just going to give you, can I give you the unleaded JV version of this? Okay, so in pre-calculus, you learned a trick about horizontal and slanted asymptotes, right? So we did these the other day. We just did them graphically. The limit as x approaches infinity, like the extreme far left edge or the extreme far, in this case, right edge of the graph. And I call this the pre-calc trick, or you could call it the degree trick, and it'll still be valid here, especially like in a multiple choice sense. What's the degree of the numerator? Degree 3. And what about the degree of the denominator? So does anybody from pre-calc perhaps remember that if the degrees are the same, long-term behavior is, Reese, what?
You take the coefficients of each half.
Yeah, the relationship of those two lead coefficients. And so what I could then say is that this limit equals 5 over 2. Now, if the degrees are different, we have to talk about some different concepts. And there is a way to, there's actually two other ways we'll talk about how to process this, but we'll save that for a different day. So anyways, great job. Have a wonderful rest of your Monday. I'll look forward to seeing you tomorrow. Please jump in and get in on presentation 1. This is your chance to come alongside Reese and say, great job, Reese, or, oh, not so great, Reese. Everybody afraid of Reese? No? Nobody's afraid? Okay. I was going to say, jump in, let him know what you think.